much.
So now may I invite Chethan Krishnan?
Yes. Okay. So shall I share the screen or?
Yes, please share your screen.
There you go. So
Chethan's title is Comments on Asymptotically Flat Space.
I slightly
Go
changed
ahead.
the title for the
Space-time.
slightly more concrete title.
Okay, good. Go ahead.
Okay, thank you.
Yeah, please.
So let me start by thanking Spenta and also Alok and his friends for organizing this conference and letting me speak here. So so the title of this talk is A New Gauge for Asymptotically Flat Spacetime. So this is some work that I've been doing with Jude during this COVID couple of years. He has been a brilliant collaborator of mine, and he is right now started his PhD at Arizona State, and hopefully 2 papers will appear soon, one of them hopefully in the next few days. So, and it's broadly motivated by some work that I had done some time ago on this thing called asymptotic causal diamonds, which I'll maybe have like a couple of slides about. So, right. So, what was, yeah. So the thing I wanted to, so the material is a bit technical. I usually don't like to give too technical talks, but the second half is unfortunately a bit technical. So, but hopefully it is not too painful. And please feel free to ask questions. I don't necessarily have to get to the end of the talk. So the basic setting is that, generally speaking, flat space holography, attempts at flat space holography are usually phrased in Bondi gauge. And I'll show you what Bondi gauge is. Very roughly, for the moment, it's the only thing we need to know is that it is a coordinate system adapted to the future null infinity of flat space. And despite its many virtues, I will argue in this talk that there exists another gauge which may be, for some purposes, more useful, or at least useful for getting some more hints about what flat space holography is or should be. I mean, I'm not necessarily claiming that this is the final gauge or whatever that is useful, but hopefully it will be useful for extracting some more information than what is accessible in Bondi gauge. And the motivation, there are a bunch of motivations. The first is that the natural observable for flat space holography is the S matrix, which has a natural ties to both past and the future. And Bondi gauge addresses only the future or the past at any, the future Bondi gauge addresses one and the past Bondi gauge addresses another. And the motivations for this, for the choice that Bondi made and Bondi and his friends made long ago, is that they are largely historical, and it's motivated fundamentally from the need to understand gravitational waves back in the day. And they wanted to look at a gauge where you could look at isolated gravitating systems from which gravitational waves were, being detected at infinity. So this whole picture has a kind of a retarded correlator feel to it, and Bondi gauge reflects that. So I think what I will try to present is a gauge which is, in some sense, has both access to future and past, and in that sense, it is more a Feynman-like gauge. So you'll see that it is kind of a double null gauge, and I'll specify what exactly it is in a few slides. So that's our, so continuing on with the motivation. So another reason why this may be of some interest is that Strominger's diagonal BM symmetry that he has identified for this gravitational S matrix, it requires a matching between the future and past, and it crucially involves the future and past. It is not just the future that you need. So what he does is he works with the future Bondi gauge and uses the past Bondi gauge, and then he tries to match them in some way. So what we will do instead is to try and have a gauge where both these things are simultaneously present, and we'll see whether it has some utility or not. So so this is yet another sort of philosophical point is that typically holography, you think of it as defined on codimension 1 screens of some type, and in flat space, if you are using only the future or the past screens, we are using only a part of the codimension screens that are available to us. We would like to have at least a formulation where both are equally accessible. So also, I think I just saw that I'm giving this talk from ISE, and there was some warning that said that the ISE WLAN is a little bit shaky. So please, if you have any, if there is if you cannot hear me, you can call me. I think my collaborator is in the audience. So if I decouple, please just let me know. So I hope you can hear me now, right?
Yes, yes, we can hear you.
So the one more motivation, so to speak, is that the holographic or asymptotic direction is the radial direction in bonding. So even though the screen is in 𝗧 plus or 𝗧 minus, the way you go to the asymptotic region is along a radial direction. And I think it is more natural to think of these as being approached along a null direction. So that's, let's say, another way to think about it. So another reason to think of it as maybe a motivation for another gauge. And the final thing, which is what I mentioned in my paper from a couple of years ago, where so the idea is that, so that was my motivations there, where from the point of view of bulk reconstruction or bulk locality or things like that. And so the idea is that just like you have ADS causal wedges from which you can reconstruct things from the boundary, you can attach causal diamonds to the conformal boundary of flat space. These things are, these asymptotic causal diamonds, so to speak, are a natural generalization of ADS causal wedges. And it's a natural starting point for bulk reconstruction in flat space. And the space of ACDs is defined by a pair of points on 𝗧 plus and 𝗧 minus. So if you have a point on 𝗧 plus and 𝗧 minus, you can, or if you have a point on in the 2 points on the boundary of ADS, which is basically 2 points on the boundary Minkowski space, then a causal diamond is defined on the boundary Minkowski space. Analogously, you can also construct, and then this boundary causal diamond can be used for reconstructing the bulk causal wedge. That's the picture that you have in ADS. So here, on the other hand, the boundary is, it has more interesting structure because it's null and everything. But if you have 2 points on the future and past, you can do almost all the things that you can do as far as bulk reconstruction is considered by constructing these asymptotic causal diamonds. So I'll just draw a quick picture here. This is not sort of my main take on this main line of development in this talk, but I just wanted to draw a quick picture here to give you a rough idea of what these are. So this is basically one of the vertices of the causal diamond, asymptotic causal diamond, and this is another one. So, and it's in 1 + 1D, it's completely easy to see what it is, and in 1 + 1D, it also happens to be trivial. But in higher dimension, it has more juice because once you send the causal diamond to infinities, the boundary structure actually becomes quite interesting and intricate. I won't have much to talk about it today, but this is another reason that I'm thinking about future and past simultaneously. Okay, so, and just to go ahead with this a bit, so the reason why these ACDs are, not just a simple adaptation of bulk causal wedges in ADS, is, so there are few, the way in which these things work out in flat space is not entirely trivial, or at least I think it is not entirely trivial. There are some subtleties, but still it works out many of the things. And there are some cases, some things which are substantively different. So, but the point is that if it has a natural interpretation of this kinematic space for flat space holography in the same sense that these boundary causal diamonds were viewed as the kinematic space for ADS-CFT. So these things have precisely the same structures in many ways. And if you also have a bulk screen, you can define regions on these screens which satisfy many of the properties of entanglement entropy and quantum error correction and various other simple and nice things. So all of those things very easily work out. And so again, I mean, this is just as broad motivation for why I think it is interesting or important to consider both the future and past simultaneously. And I will show you one picture from a paper that I wrote with Jude and another junior student, 𝗦𝗵𝗶𝗿 of mine. And the only reason I'm showing you this picture is because compared to this is significantly more beautiful. And that's one of the strengths of, working with junior collaborators. And this is, so this thing here, so this is in the conformal coordinates, this picture. So this thing that you see at the edge here is actually the picture of a asymptotic causal diamond. And this blue line that you see here, this is actually it's a straight line in Minkowski space, and that's the waist of the causal diamond. Okay, so, it's just that because it is conformal coordinates, it looks good here, but it's really the same thing. And if there is matter inside, you can actually show that this quantum extremal surfaces, etc., are perfectly well defined, and they get pulled in because of gravity, just like they do in ADS. So all of these, we wrote this in the context of this page curve discussion. And so you can argue for the existence of phase transitions and all that kind of thing in this context. So anyway, so this is all largely just motivation for why it is perhaps reasonable or interesting to consider future and past 𝗧 plus and 𝗧 minus in flat space seriously, if we want to think about holography in some sense, or at least it may be of some use. Okay, so that's basically the general motivation. Now I'm going to go and talk about the actual stuff. I'll pause for a second and take any questions if anybody has anything to ask. Okay, so so if there are no questions, so the basic idea is just that first we try to look for a double null gauge, double null coordinate system, and you know, you can justify it in somewhat more fancy ways, but it's kind of should be intuitively clear that a double null coordinate system will simply have this gauge imposed on it. So, but the point about double null coordinates is that they're not a complete characterization of a coordinate system, because there are just two conditions in a space-time with many coordinates. So you need to choose one more set of enough number of more conditions so that you actually have a perfect, well-defined gauge. And the thing that we will choose, because we want to sort of retain the symmetry between the future and past, is we'll set GUA is equal to GVA. And this is what we'll call the special double null gauge. And just to contrast with Bondi, if you're familiar with the Bondi gauge, Bondi gauge is basically something like this. Okay, so this is the definition of Bondi gauge, and it's also, this is only 3 conditions in 4 dimensions. So they also impose a determinant condition. Note that our condition, because this is 2 conditions, A is the coordinates on the sphere, and these are 2 conditions. This is equal to 0 and this is equal to 0. So altogether, we already have 4 conditions. Okay, so this is the 4 conditions are already imposed. Here, on the other hand, you also need a determinant condition on the sphere metric in order to get some traction. Okay, so one way in which one particular ansatz, or you can write this is a metric that one can write down which satisfies this gauge. Okay, or there is enough number of functions here. So this 𝗦𝗵𝗶 has so there are two components for this. Then there is 3 components, 3 or 2 plus 3. This is 2 plus 3, 5 plus 1. Yeah, this is correct. So there are 3 components here. There is 1 component here, and then there is 2 components here. So there are 6 coordinates here. And similarly for Bondi, you have 1 function here, 1 function here. This is 2, and then there is 2 here, and then 2 here. So that looks like it is 2 plus. No, this is 3 and 2 and 2. This is 7. But then there is a determinant condition on this metric of this 𝗦𝗵𝗶. So you end up finding that it's actually 6, as you would like. So there are 6 functions worth of 6 functions here. So that's basically our gauge, and this is the setting in which we are going to work. Okay. So, so note that we have done nothing so far. All we have done is process some coordinates. There is nothing about flat space. There's nothing about anything here. It's just a coordinate system for writing any metric that you might like in 4 dimensions. So, and so the first thing we would look at is that, so let me just flash you. So yeah, so I want you to just look at, this is Minkowski space in double null gauge, if you like. So in Minkowski gauge written in double null gauge, we can we can find out the asymptotic action of the Poincare transformations, and for Poincare transformations in the boundary of this flat space, and it turns out to be it's somewhat similar to what one does in the case of Bondi gauge, and you find that the translations act like this, and the boosts and the rotations act like this. Okay, so this is just something that you can figure out. And so the question, so I mean, in some sense, the big question in my mind is that are there any interesting unitary theories that live on this 𝗧 plus union 𝗧 minus, where the Poincare acts in this way? Because an action of Poincare is quite nice in some way. So maybe there is a way in which you can just use this if you have enough imagination to guess the kind of theories that are going to be interesting on this pair of spaces. So I mean, it may not be the best way to formulate this might be to go to analytically continue in some way or something like that. But I'm saying that this is, if you have an interesting answer to this question, I think we are quite a ways to understanding it's the analog of knowing what a CFT is in the context of ADS CFT, I would think. So yes, so that's the thing. But of course, it is probably too ambitious. And our goal in this talk is, in some sense, much less ambitious. So I flashed this slide too fast, probably, but it's it's just there's nothing to there. It is just the asymptotic action of point carrying on these coordinates, and you can just believe me that those things are, you can figure them out, and yeah, the slides are there. So yes, and so our goal in this thing is. So what we would like to understand is we want to understand the asymptotic behavior in the special double null gauge of our metric, and we would like to solve Einstein's equations, etc., asymptotically, figure out BMS or something other symmetries. These are our broader goals. So, and we try an expansion of this form. Okay, so these are some of the metric functions. I mean, there are others. So 2 of them I'm writing here. So, and these are the fall-offs that you have. So, well, this gamma ZZ is actually 0. Because the sphere metric is, ZZ, it only has support on gamma and ZZ bar, but I'm just writing it for illustration. So, so this is the kind of fall-offs that one can try. And so the first thing we can note is that because we are working in U and V coordinate, our holographic direction is null. Okay, so we are going to 𝗦+, but not along R. And clearly a similar expansion can be done in the past direction as well by doing an expansion in 1/U. Okay, so this may be seen similar to the past Bondi gauge. And this, morally it is similar to past Bondi gauge, but there's a crucial distinction, which is that in Bondi gauge, and the gauge I'm putting in quotes, because there are really 2 separate gauges in the future and past. And here we only have 1 gauge. And what we are really doing is we are doing 2 expansions for the same gauge at 2 boundaries of spacetime. So the future boundary of the 𝗦+ and the past boundary is 𝗦-. So we have only 1 gauge and we are doing 2 expansions and 2 boundaries, as opposed to a Bondi gauge where there is a future Bondi gauge and a past Bondi gauge, which are 2 different gauges. All right, so that's one thing. And so now we start systematically imposing. Our goal is to see what the asymptotic symmetries are, whether we can make connections with the things that are already known in Bondi gauge or Stecker-Hansen or any of the other gauges. That's our goal. So to impose asymptotic flatness, so asymptotic flatness here means asymptotically Minkowski. And so we can start by checking what happens if we demand Riemann is equal to 0. Okay, because Riemann, so oftentimes this is phrased as a statement that Weil tensor vanishes at the boundary of spacetime, but that's largely because of the fact that Riemann contains Ricci and Weil. So if you demand Einstein's flatness, Einstein or Ricci flatness, then all that is left is the Weil. So this is, you can think of this as the equivalent of sometimes in the Bondi context, people will talk about the Weil curvature vanishing in some ways. So yeah, so we are going to demand this, and so yeah, so one may be forgiven for thinking that this would force us into the form of Minkowski space in our gauge, where we write U is T minus R and V is T plus R. Okay, so if you just demand Riemann flatness, you would think that you would get Minkowski space back. But that is not quite what happens. Note that we are imposing it asymptotically in this sort of a fall-off, and this is not what happens. What happens instead is that this Riemann flatness allows a whole towers of undetermined integration constants that are purely functions of the angle Z and Z bar in the fall-off coefficients. So what I mean to say is that these coefficients here, they still allow the possibility of arbitrary, not all of them, but 3 towers of them, basically. 3 towers of them allow integration constants that are, I call them constants, but they are functions of the angle Z and Z bar. So that's what Riemann flatness fixes for you. There are some systematic exceptions, as I said, but this does not affect our story, so we will not emphasize them in this talk. And in fact, these integration constants persist even when we solve the Einstein equations asymptotically. So one way in which this manifests itself is that unlike in Bondi gauge, here the Einstein's equations typically only determine the U derivative of the fall-off coefficients. They don't determine them algebraically to higher and higher order. Typically, Einstein's equations, if you have some integration data and you put something, so that if you prescribe enough integration data, what happens is that it will fix it to all orders. But that's not what happens here. What happens here is that as you go to higher and higher orders, you keep generating these integration constants, which are functions of just the Z and the Z bar. So the fact that they show up even when we demand Riemann flatness is a hint that these are trivial gauge parameters, which can be set to 0 by trivial diffeomorphisms. Okay. In fact,
there is a question, Chetan. Yeah. There is a question from Isa Bhopal. Would you like to take it?
Yes, please. Go ahead. Yeah.
Go ahead.
Hi, Chetan.
Hi.
Am I audible?
I can hear you, but I think a little louder may be better.
Okay. Can you just go back a few slides?
Sure. Here?
Yeah, sir. So here the expansion you are only writing in terms of V. So
I'm writing in terms of U. So I'm going in the direction of V. V is the holographic direction here. I'm going to V infinity. So which is future, infinity, sky plus. And my coefficients are arbitrary functions of U, Z, and Z bar.
Okay. And so is like that at any point you would also like to know how it behaves with you or not?
Sorry, I can't hear you.
Will you also like to know how it behaves with you or
yes. So I will also look at what happens in past null infinity. So I will also look at what happens in past null infinity, and here I'm just looking at future null infinity. I'm expanding along the future direction and doing things, but I can also do it along the past direction by expanding along U and going to minus infinity. Yes, I can do it. And in fact, I will do that.
Okay, thank you.
Yeah. So yes. So the fact that even biennial Riemann flatness leaves you with these trivial gauge parameters, I think we'll find multiple pieces of evidence that this is an indication that these are trivial gauge parameters, and one of them is the fact that Riemann flatness just leaves you with this. Okay, and in fact, we discovered it actually by as a contradiction of Birkhoff's theorem. So we were trying to find what happens in Schwarzschild. What is the analog of the spherically symmetric vacuum solution in flat space? And we ended up finding these parameters, and we were confused. So these trivial functions which were confusing. So in the end, it turns out that even if you demand Riemann flatness, you find these, and these are trivial gauge parameters. And so one way to get some confidence in this, and this is a slightly technical way to do it, and only the result is important to us, so you can find it in our paper if you want, is that in Einstein gravity, you can explicitly compute these surface charges. These are things that Iron Wald and various other people have defined. And we can plug our expressions into their formalism, and you find that these parameters do not show up in the asymptotic charges one defines. And so that's one reason to think that they're trivial gauge parameters. I'll have more to say about them in the few slides. But for now, with some minor choices analogous to some of the choices in Bondi gauge, these integration constants that correspond to physical data. Okay, so there are so the way, when you do this solve Einstein's equations, what do you call it? When you solve Einstein's equations, asymptotically, you find data analogous to what you find in Bondi gauge. And in fact, apart from these trivial integration constants that I talked about, there is also data of this form. Okay, so these are the data that we have. And these are analogous to the shear data, the mass aspect, and the two angular momentum aspect data. Okay, so these are the things that one has. And we can also define a news in the same way that essentially the same way that one defines this. So this lambda shows lambda 2 is a second coefficient in the expansion of the lambda field, and alpha is the thing that is there in this here. So this is the alpha. So I have some expansion for omega, some expansion for lambda, and some expansion for alpha A. So the omega AB expansion is one of the terms in that is basically what this shear is. And the lambda is one of them is this, and this is the quantity that shows up in the angular momentum aspect. Okay, so to give a flavor of some of this, let us write down the Einstein constraint on the mass aspect, which happens to be quite simple. And this has some structural similarity to the Bondi mass aspect constraint as well. One crucial difference is that what we have is a second derivative, and this is consistent with what I was saying before about we always seem to be getting these extra trivial integration constants on top of all this. So, and a similar but more complicated expression can be written for the angular momentum aspect as well. Okay, so so that's basically that. I'll come back. I'll have more to say about these things if I get to the end. So the point is that asymptotic symmetry. So the thing that we would like to compute, the standard thing that we would like to compute is asymptotic symmetries and BMS. And this is somewhat of a technical enterprise. But the conclusion is, in some sense, but it's quite straightforward. There is nothing particularly, it's like you just follow the formalism or the calculations that Barnish and Troissart have done in the case of Bondi gauge. and we can straightforwardly adapt it to our situation and try to do the calculations. And you find that these asymptotic killing vectors that were defined. So the asymptotic killing vectors are basically solutions to L psi g mu nu equal to some order fall off, and the choice of the fall offs is where the sort of the game is. And well, I mean, actually, in our case, it is actually fairly straightforward once you play around with it. But and you find that once you choose a set of fall offs, you basically find that the killing vectors that you're left with basically have some amount of freedom, and these freedoms are what are basically called super translations and super rotations. And you can define a sort of a commutator of these things, and you have to, there are commutators and there are some modified commutators, etc., that one has to define. And once you compute all of those things, we find that even though the details in which the calculations arrange themselves is quite different, at the end we have precisely the same information as what happened in the case of Bondi gauge and so on. So one can think of that as either encouraging or disappointing, because if you're hoping to find that you're hoping to find something more, maybe this is not finding BMS again may not be the greatest thing. But there is one interesting point, which is again related to these trivial integration data.
So,
sorry,
Chetan,
yes.
Before you go on to that point,
yeah,
Alok Lada had a
yes.
question.
Chetan, hi.
Yeah.
I just had a small question that since you did not fix the sphere metric, right, at infinity.
Yeah.
So that,
I think, in this choice, when I'm saying it here, I'm fixing the sphere metric.
Okay, because the news, otherwise the definition of news is not, you have to add the extra term.
But we have a discussion of the more general case also in the paper. So what actually happens is that in the double null gauge, the sphere so it just becomes, the freedom that you have just becomes a function of Z and Z bar. It turns out to be the case. We have not fully understood why that happens, but
But in that freedom, I mean, the definition of news in general is not 12, but there's extra term. There is the
right. So this is here I'm fixing it to be gamma ZZ bar, which is the sphere metric on this thing. So this is, I'm trying to be as close to BMS here.
Okay, thanks.
So, and also, so there are a couple of more comments. I think, maybe you can, I can tell you at the end. So there is so there is a question about log fall offs that one has to worry about, because, one might worry that, so typically in a Schwarzschild, if you write in Eddington-Finkelstein or something like that, you actually find that there are log terms that show up, right? So, but we have not introduced any of them. We are kind of expanding in 1 over V, but we're working with, so this looks like we are assuming, we are working with an analytic expansion at infinity. So is that allowed is a question that one could ask. But it turns out that there is an interesting resolution of that because of the presence of these trivial integration constants. But yeah, it will be...
And large positive V, right? You're expanding at large positive
large positive V, that's right. Yeah, large positive V, and I'll also do that in the large negative U. So yeah, so the one difference in the when we get the BMS algebra is that unlike in Bondi gauge, together with super translation, super rotations, these asymptotic killing vectors come with an infinite towers of unfixed trivial diffeomorphisms, which are precisely in one-to-one correspondence with the trivial integrations that we saw when we are doing the follows. Okay, and so one can explicitly show that these trivial AKB coefficients have precisely enough freedom to set the corresponding trivial gauge parameter 0 if we choose. And this can be, so this can be seen by first determining the action. That's a technical comment. So it's just true that, AKV coefficients, which are these infinite towers of these trivial AKV coefficients that show up, can be one-to-one mapped to the trivial gauge parameters, which is another reason to think that, to be, convinced that they are just trivial diffeomorphisms.
Chetan, how long will you take now?
I think my real number of slides is still 30. So I think that I can wrap it up in another, can I go to 11:30? Is that okay?
11:30?
It's 11:18 now. If I have 11:30, I can, so yeah, I mean, okay. I mean,
okay.
How much more?
Try to do it in 5 minutes.
Okay, sure. I'll try.
All right.
So yes. So then there is a second question is a similar discussion for Sprite Plus applies also to the past. And so in order to define a classical scattering problem, we need to match the integration constants that Scri plus minus and Scri minus plus across I naught. This is sort of the future past antipodal matching of Strominger that we have. But there's a natural way to do that in our case, which is that we basically demand asymptotic CPT invariance on all solutions. And the asymptotic CPT invariance basically acts like this. And so that lets us match these integration constants. So I'm writing this C and C tilde. So C is for the future integration constants and or the data, and the past is for the the one in the past. So they have to be matched in this way. And so the reason why sometimes in the case of standard BMS discussions, people often match it as C Z bar is equal to C tilde of Z and Z bar. And the reason for that is that because they have two different coordinates in future and past, so the Z that is defined in the past is actually with respect to the south pole. So that's where they don't have to do this inversion. In our case, we do have to do, we have only one coordinate system, which is this gauge. And so because of which, this is the mapping that we have. So I want to emphasize that it is not an extra complication. It's just that the extra complication is not visible when you work with two different coordinate systems in the case of bonding. Okay, yeah, so this is not very important. So yeah, so let me come to the, so the general structure of when we integrate these constraints is that we have, so I'm just writing a schematic expression for a general constraint, how the Einstein constraint gets solved. So what happens is that when you do something like this, so the general solution is you have an integration from scribe plus minus up to u, and so you have, so this is some, so this is the right-hand side of the constraint, whatever that might be. And this is the general form that it takes. And we can demand that the integral here converges at the lower end. That's one way in which, for instance, in the case of the Bondi mass aspect, sometimes this fall-offs called these Christodoulou-Kleinerman fall-offs are often invoked. And so, I mean, at least in the Bondi mass aspect, this argument works. And you say that, okay, this integral has to converge, and that, the fall-offs that Christodoulou and Kleinerman suggested would accomplish that. And then you have this, then this is basically the, this is the, these are the two pieces of data that you have. So, but I think that in our, I think that it may be it may be more interesting or more useful or probably more generally valid to consider the possibility that in this integration, which is happening at spatial infinity, scribe plus minus, okay, so it's close to spatial infinity, to put a cutoff here, and then if you have a cutoff here, the whatever is the divergence or whatever it is, that you can absorb into this trivial integration or the integration constant that you have sitting here. So, and I think that it is this renormalized integration constant that should really be matched between future and past. And the contribution from the lower end of the integrand can then be simply viewed as renormalizing the bare integration constants. And I think that the fact that this is the structure that universally shows up in our gauge, I think is, I think it is very suggestive in some sense. And I think that this is the, probably this structure, I think may be of some use in understanding flat space holography. Note that this is basically a light ray-like integral. Okay, so I think that's, I think I'll go, I can say a little bit more about that, but let me go to the sort of the concluding couple of slides. So, so yeah, so the basic message is that it may be useful to think of scribe plus and scribe minus together as a natural habitat of the hologram of flat space, or maybe it's some sort of analytic continuation of it. And can we find an interesting unitary theory there where Poincaré BMS act in the way that we have described? So, so the quick question is, what are the natural operators? If you want, if you want to push this in some ways, what is the natural operators that might live there? And so one natural guess is this light ray operators, light ray-like operators that I mentioned here. Okay, so these things are somehow living in I0, if you want. Well, it's not clear where they live. It's basically just, it has only angle dependence. So, and but the point is that these integrals are from past null infinity on the scribe plus to some specific point on scribe plus. Okay, so these are sort of light ray-like operators which are integrated between some point on scribe plus to spatial infinity. So on the null generators of scribe. So, and they seem like natural candidates for various purposes. And what happens if we solve, so one of the things that we have not done completely yet is that, the first thing to do is first solve Einstein instead of trying to solve scalar field theory. So what happens if we solve free scalar field theory in Minkowski space in double null gauge? So, and this is something that I'm doing with my student, 𝗦𝗵𝗶𝗿, who's probably in the audience. And an object called the Riemann green function naturally incorporates the sum of the structures that shows up in the case of Einstein. So, and I have a suspicion that the holographic data that is captured by this, note that this is entirely holographic data. This is purely on the boundary, the scribe. Okay, so, and can we view this holographic data as analog of some form of normalizable and non-normalizable modes in ADS, or some such way of, exhibiting that? So I'll stop there, but I have a few more slides. If there are any questions, I can answer them. Thank you.
Okay, thanks, Chetan. 𝗦𝗵𝗶𝗶 has a question.
Yes.
𝗦𝗵𝗶𝗶, could you please? 𝗦𝗵𝗶𝗶?
Maybe she already asked the question.
No, no. No, not really. There is a question in the chat. Maybe I'll read it out.
Please.
Is it not expected that the symmetry will be same, as finally you will have U, Z, and Z bar, where transformations will work? That's a good question.
What is it? Sorry. What is
that was the question. It's in the chat actually. Is it not expected that the symmetry will be the same?
Yes, it is the answer. The fact that it is BMS. I mean, if you find something other than BMS, or if it is something smaller than BMS, then I think it clearly means that something is wrong. At least we should find BMS, and we do.
Okay.
So the question is, but we have tried to adjust our, we have not worked with as general as a expansion as one can have. So we could try more general, so there are some minor choices that we have made, as I mentioned here, so that we are not working with some, so we first wanted to kind of establish that we have some common ground with the BMS literature. So in order to do that, we made some guesses, or not guesses. I mean, it's like there are, for instance, we have worked with we have not allowed, as Alok was saying, that we have not allowed the possibility of an arbitrary conformal factor on the sphere. So those kinds of simplifications. So those kinds of simplifications, we expect they will not lose BMS. So we made those simplifications, but there are only two or three such simplifications. And once you do that, you get BMS. So that's kind of the starting ground. So in that sense, yes. I mean, we have engineered, engineered is too strong a word. So we have chosen our, we could work with more general these things and expect to find probably bigger symmetries, but it remains to be seen.
𝗦𝗵𝗶𝗶, is that, would you like to say something? Because you were not audible.
No, Sweta, it's okay. I heard what Chethan said.
Yeah.
So I was just, okay, thanks.
Yeah.
Okay. So let me go to there are a couple of more questions. So let me invite Shiraz to ask this question. Shiraz?
Yes.
Hi, Chethan. A couple of quick things. Right at the beginning of your talk, you talked about these Ryu Takanagi kind of surfaces that ended at scribe plus and scribe minus.
Yeah.
So in your picture, these surfaces compute the entanglement entropy of what with what?
So
is it one part of part of the sphere with the other part of the sphere, or yeah?
So I think it is first. Let me talk about that in the case of Minkowski space. So if in Minkowski space, if you're constructing the base of these causal diamonds will intersect finite radius screens. So, and that's one way in which you can define subregions on the screen. So, and the claim is that the minimal surface that connects these minimal surface or RT surface, whatever that connects the boundaries of those subregions are basically measuring, so they satisfy things like strong subadditivity or any of the holographic entanglement inequalities. So that's the reason why I'm thinking that they're capturing, so the properties that they capture are precisely the properties that one would expect from tensor factors of theories. So that's the reason why I'm thinking that they are entanglement entropies.
So I didn't understand. Are they entangling one part of the sphere with another part of the sphere?
So the what is entangling, I think it is a risky question. I think I would not to answer it yet. So what I would say is that these minimal surface areas that they compute satisfy properties of entanglement entropy. That's all I'm saying. So That's the sense in which, so which I think it is some sort of coarse-grained entropy where the scale of coarse graining is defined by the size of the screen. I think that's what they're ultimately computing, but a precise definition we don't have. So but the point is that, but they satisfy these properties of entanglement entropy. All these holographic, strong subadditivity, I don't know. Now I forget. It's a couple of years now. So that's all. I mean, it's not a stronger statement than that.
Okay, thank you. Spencer, do you have time for one more? Or do you need to move on?
Yes, please.
Okay.
Go ahead.
Again, I apologize if I didn't understand correctly, but when you talked about the mass constraint equation, you had a term with a second derivative of u.
Right.
Now, the way I understand that mass constraint equation is that the change in mass is measured by the radiation that goes out.
Right.
And if that understanding is correct, it's like a first derivative thing, right? Its change is equal to something. So I couldn't understand why you got second derivative. Or is the integral of lambda2 the mass?
The integral of
is lambda2 the mass, or is
no? It's du lambda2, which is more.
Then I don't have a question. Then it's just a derivative of mass is equal to.
Yeah.
Okay, thank you.
So the extra term that shows up is what I was calling a trivial integration.
Thank you. Yes.
Yeah. Okay, amitabh. Would you like to ask your question?
Yes. Hi, Chethan.
Hey, how are you?
Yeah, fine. So, Chethan, your coordinates cover spatial infinity also because you have both u and v.
I think so. Yeah, but I don't have. These are things which probably you guys know better. I think so. I don't know how to think of. For instance, time like infinity. I don't know what to say about it.
No, not the time like. It's spatial infinity only.
Okay, go ahead. Yeah.
So you have super rotations at null infinity, both u and v. You think?
Yes, I do. Yes.
So you think you will have super rotations at space infinity also?
So we started out with something like Ashtekar-Hansen, but I have not really tried to relate them. We need to do a asymptotic coordinate transformation to connect it to this thing. So I don't have a very strong opinion on it. But one thing I would say is that our coordinate system seems to automatically tie also to because of this kind of equations that I was mentioning. So this kind of equations, this is the structure that one often sees. So and that seems like this integral at minus infinity is basically an integral that starts at I0. So there is something about I0 that is intrinsically built into this formalism. So even though we are looking at future and past gauge. So I don't have a clear answer. I don't know basically. Yeah.
Thanks.
Yeah. Okay. Alok.
Yeah, Chethan, hi. Yeah, so just one small question, actually related to what Amitabh is asking. So when you do, you use Cry plus Cry minus, but naively when we do conformal compactification with these double null coordinates, we get these Penrose's boundaries, right? So where the Cry plus Cry minus are really touching at a point I0. So there, we never get like disconnected, as far as I know, in this conformal compactification with the coordinates you use, disconnected Cry plus Cry minus, right? And
but I'm not saying that they're disconnected, right? I'm in fact matching them across this.
But so they're connected at I0. And what is I0 for you? Is it a point or a sphere?
It's a point.
But if it's a point, then I guess.
I think that's the reason. So I think that's the reason why I'm saying that it's better to probably think of this minus infinity here as being regulated in some way.
Right. So it's different than Bondi, I'm saying, where if you blow up I0 also, you get a hyperboloid which is smooth, right? You are getting these Penrose boundaries, which are really, it's not quite Scry the way we say Scry in Bondi. That's all I'm saying.
Oh, I see. Okay, that's an interesting point. I didn't know that distinction actually. Okay, yeah. Thanks. So maybe I'll talk to you. Yeah, that's So that might explain some of these things actually. I see.
Thanks.
Yeah.
Okay, we'll take the last question now from Rita. Please go ahead and ask your question.
Yeah. Okay. Hi. Yeah. Thanks for the talk. So these trivial gauge parameters that you mentioned, like demanding the Riemann flatness, that you get it at asymptotic infinity. Since they are function of z and z bar, you said, so you will need probably large gauge transformations to make them zero, right?
Yeah. These are asymptotic, large gauge they are transformations at boundary, right?
Yeah. So then, like setting them to zero, wouldn't that change like the take you from one asymptotic flat solution to another?
So, but their charge is zero. So that's one of the things that I mentioned here, somewhere here. Yeah, so if you compute their charges, they are 0. So they don't contribute, they don't come up in the charges. So that's the sense in which they're So that's basically the asymptotic symmetry group, right? So you have this large gauge transformations modeled out by these trivial gauge transformations. So these are trivial gauge transformations. And I think the reason why I think your question comes up is because I think in most cases, for instance, in standard Bondi gauge, you actually, even though we say that there is trivial gauge transformations, like the trivial gauge transformations just aren't there. So when you write down you just say that they don't arise at all. So it's the entire set is just the super translations and super rotations in Bondi gauge. Here, but on the gauge, we have the trivial gauge transformations and they are going away at the end.
Okay. Thank you.
Okay, so let's thank Chethan again for a very interesting talk.
Thank you.
And now we